In this video, I'm going to explain what's really happening beneath the surface of Long Valley's supervolcano in California, why it matters, and what it means for people who live there. This is Geohazards Explained. Right now, underneath one of California's most popular ski resorts, a supervolcano is showing new signs of life. Earthquake swarms are clustering near Mammoth Lakes. The ground has been rising for years, and invisible volcanic gas is seeping up through the soil, killing entire forests. This is Long Valley Caldera, and most people have never heard of it. Long Valley's founding eruption was more than 2,000 times larger. Roughly 40 miles east of Yosemite, about 200 miles east of San Francisco, and 250 miles north of Los Angeles. It measures 16 by 32 kilometers. That's 10 by 20 miles, making it one of the largest calderas in North America. The USGS classifies it as a very high-threat volcano. The caldera formed about 760,000 years ago during a cataclysmic supereruption that blasted approximately 150 cubic miles of magma from a depth of about 4 miles beneath the surface. The USGS describes this as a caldera-forming eruption considered a supereruption. Rapidly moving pyroclastic flows, superheated avalanches of ash and gas, covered much of east-central California. And here's the critical point. The magma system beneath Long Valley is not dead. Hot springs, fumaroles, and geothermal vents dot the landscape. A geothermal power plant inside the caldera generates enough electricity to power 40,000 homes. The system also connects to the Mono Inyo crater's volcanic chain, which extends 25 miles northward to Mammoth Lake, and that chain has erupted as recently as 300 years ago. The modern era of unrest at Long Valley began in 1978, when a magnitude 5.4 earthquake struck 6 miles southeast of the caldera, ending 2 decades of relative quiet. Then, in May 1980, the same month Mount St. Helens erupted, Long Valley experienced 4 magnitude 6 earthquakes, 3 of which struck on the same day. Scientists immediately began a comprehensive re-examination and discovered something alarming. The center of the caldera had risen almost a foot since the summer of 1979. The ground was swelling. Magma was on the move. Throughout the 1980s and 1990s, earthquake swarms continued with regularity, sometimes hundreds of earthquakes per day. In 1992, a magnitude 7.5 earthquake hundreds of kilometers away in Landers, California, triggered an abrupt increase in seismicity at Long Valley, a reminder of how interconnected these systems can be. A well-documented swarm in September 2014 drew close USGS attention, and during that period, the resurgent dome had been uplifting at roughly an inch per year since late 2011. Now, the USGS California Volcano Observatory published a report on January 6, 2026, noting that 2025 was a seismically uneventful year for Long Valley, one of the quietest on record. But quiet doesn't mean dead. As of today, February 28, 2026, the Southern California Earthquake Data Center shows renewed activity. On February 25th alone, 4 earthquakes clustered within 2 kilometers of Mammoth Lakes at depths around 6 to 7 kilometers. That's shallow, and that's significant. On February 26th, a magnitude 2.0 event struck 25 kilometers west-northwest of West Bishop at 12 kilometers depth, along with additional small events near Mammoth Lakes. Over the past week, we're seeing a clear uptick in microseismicity compared to the quiet baseline of 2025. If quakes increase and multiple deformation instruments shift together, that's when scientists start paying much closer attention. At Long Valley, the USGS currently operates a network of 9 tiltmeters and 46 continuously recording GPS receivers. Tiltmeters work like an extremely sensitive carpenter's level. They can detect a change in slope equivalent to placing a single dime underneath one end of a 1-kilometer-long beam. That's a tilt of 1 microradian. What have they recorded? Between 1978 and 1983, the resurgent dome, the central bulge of the caldera, began rising dramatically. By early 2000, total uplift had reached nearly 2.5 feet, affecting more than 100 square miles. The USGS confirmed through joint INSAR and microgravity data that magma is unambiguously the cause of this uplift. A renewed inflation episode began in late 2011, with GPS and INSAR data showing uplift rates of up to 15 millimeters per year beneath the resurgent dome, consistent with a persistent elongated spheroidal magma reservoir approximately 7 kilometers, about 4.3 miles, beneath the surface. A 2022 Stanford University study also found that Sierra Nevada snowpack weight actually opens and closes fault conduits like a valve, modulating CO2 release, meaning climate change and drought could alter how this volcano breathes. In the early 1990s, trees began dying on the flanks of Mammoth Mountain, a young volcano sitting on the southwest rim of the caldera. USGS and Forest Service scientists discovered that the roots were being suffocated by massive amounts of carbon dioxide gas seeping up through the soil from magma deep beneath the mountain. Today, areas of dead and dying trees total more than 100 acres. In the tree kill zones, CO2 makes up 20 to 95% of soil gas. Normal soil contains less than 1%. The total CO2 emission rate at Mammoth Mountain has been measured at close to 300 tons per day. At the Horseshoe Lake tree kill area alone, measurements have averaged 110 metric tons per day. The USGS monitors CO2 concentration continuously year-round at Horseshoe Lake and conducts biannual flux surveys. Together, the degassing areas around Mammoth Mountain contribute more CO2 to the atmosphere than other volcanoes in the western United States, though emissions remain low compared to actively erupting volcanoes. Long Valley's geologic record shows this system is capable of a wide range of activity. Beyond the 760,000-year-old caldera-forming supereruption, the Mono Inyo crater's volcanic chain has produced eruptions every few hundred years over the past 4,000 years. Mammoth Mountain itself was built by a series of eruptions ending about 50,000 years ago. Eruptions occurred along the Inyo craters and Mono craters as recently as 600 years ago, and small eruptions occurred in Mono Lake sometime between the mid-1700s and mid-1800s. That's within the period of European settlement of California. Of the roughly 20 eruptions over the past 5,000 years, all but 3 were explosive in nature. The 3 exceptions were effusive Hawaiian-type eruptions, the Red Cones eruptions about 5,000 years ago, the Nugget Island eruption about 2,000 years ago, and the Pauha Island eruption just 300 years ago. All were small to moderate in scale. This tells us the system's default mode is explosive, and it has been active well within human history, all feeding real-time data to the California Volcano Observatory. The USGS long-term outlook states that in the absence of unrest, meaning no earthquake swarms, no ground deformation, no gas emissions, the odds of an eruption occurring in any given year along the Mono Inyo chain are 1 in a few hundred. That's comparable to the odds of a great magnitude 8 earthquake along the San Andreas Fault. Unrest can temporarily increase those odds, depending on the nature, intensity, and location of the activity. Future eruptions are more likely to occur along the Mono Inyo chain than from within the caldera itself. They're likely to be explosive but small to moderate in size. For the Mammoth area specifically, the most likely eruption scenario is a lava fountaining eruption that builds a scoria cone and feeds lava flows. The USGS also notes that only about 1 in 6 episodes of unrest at large calderas worldwide actually culminates in an eruption. Here's the bottom line. Long Valley Caldera is not about to blow up tomorrow, but it is restless. It is monitored for a reason, and the recent uptick in seismicity near Mammoth Lakes, after one of the quietest years on record, is exactly the kind of signal change that warrants attention. Watch for convergence, seismicity, deformation, and gas changes moving together. That's when the picture changes. Geologic hazards can't be eliminated, but they can be explained. And when we understand how the Earth works, we make better decisions about where we live, how we build, and how we prepare. If this helped you see the ground beneath your feet a little differently, Consider subscribing for clear, honest explanations of Earth's most powerful processes. This is Geohazards Explained, and I'll see you in the next one.